We often fly through thin air to get to places faster, but in the future we might travel through no air at all, even here under the sky. So today we'll be looking at the concept of the vacuum train, which is a very large category of vehicles for use on and off planets, including one designed for getting off planets like a mass driver, and more recently a strangely controversial subject. I'm assuming some of this is because of Elon Musk's Hyperloop, and all sorts of videos pointing out real or perceived engineering or economic issues with the design or its planned implementation, along with rebuttals. I'm going to preface this video by noting that the Hyperloop is one type of vacuum train, indeed one running on very low pressure rather than a full vacuum, and there are many designs for many purposes, both of Hyperloops and of the wider category of vacuum trains, along with pneumatic options like scaled-up versions of the message tube systems a lot of office buildings or banks have. Some, like the gravity train, aim to move objects around a large body with virtually no energy expended. Some are akin to the Hyperloop, while others are meant to run around planetary-scale megastructures at near-orbital speeds. There are a lot of points of overlap in basic function with the Hyperloop, so we will address some of the common concerns raised about that where it is relevant. I should emphasize that some of those are quite legitimate concerns, though others are less so, and none of those criticisms or rebuttals gain or lose validity based on whether or not Elon Musk suggested building it. There's around a dozen startups that were seriously looking at the Hyperloop, and it's back in the news because one of those, Hyperloop One, shut down recently, and until last year it was called Virgin Hyperloop and had Richard Branson as a backer rather than Musk, so a different space mogul entirely. Also, the core concept of vacuum trains is over a century old, and atmospheric or pneumatically propelled railways are even older, and has collected many problems and concerns as a concept in that period, along with many solutions. The first and most obvious is in the name, vacuum, because the biggest limitation on speed and guzzler of fuel is shoving your transport through air or water. In the absence of friction or drag, once you got your car up to speed on a freeway, other than slowing going uphill a bit and speeding up on the way down, it would stay the same speed the whole time and need no more fuel. An object in motion stays in motion, and at rest stays at rest, unless acted upon by an outward force. This is Newton's first law of motion, and the reason why you don't need cruise control in space. You only burn fuel to speed up, slow down, or tweak your trajectory. If Earth were airless, ignoring that your car's combustion engine wouldn't work, or would need to carry an oxidizer, your mileage would more than double, as generally speaking, you have a bit more drag than rolling resistance on a road. We can lower that ground resistance a lot too, especially on a rail system, where we aren't worrying about the vehicle needing to rapidly stop or change lanes or skid on ice. Friction with the road surface costs fuel but adds safety in maneuvering and reaction. What's more, air drag generally rises with the square of velocity, so if we try to go 10 times faster, we are getting 10 squared or 100 times the drag, and things are getting even worse as we hit the sound barrier, which is why we mostly try not to. We can cheat in a tunnel though, by lowering the air pressure or by moving that air the same direction we want to go, like being carried along by water in a pipe, in which case the dynamics change. Never try to think of any vacuum train as being in true vacuum. As we discussed in Zero Point and Vacuum Energy last year, that does not exist, and honestly even near vacuum isn't worth obtaining in general. Never think of them as zero energy either. You always have some sort of friction, and for this same reason, don't assume one running around the outside of a space megastructure like our Ringworld or Topopolis is going to be moving at near light speeds or even close. Their functionality is a lot like that of better roads. We figure out the economics based on if the fuel savings from using an improved roadway exceed the cost to make and maintain it, and combine that with the time savings. Time cost or opportunity cost cannot be ignored. If I can get somewhere faster, I can get more done. Though we don't want to assume someone making $40 per hour driving an hour into work who can commute in 1 hour each way, and cuts that down to 1 hour for the round trip, is truly saving $40 a day, or losing an hour by not doing so. Your transport time can be productive for work or relaxation. Audiobooks come to mind, and all the more so as we move into an era of automated driving, though that's been common with trains and planes for a long time. You relax and nap or read a book or the paper while stuffing yourself into a small seat and hoping that toddler sitting in the row next to you is feeling sleepy. This is not an episode on the merits of self-driving cars or mass transit, but we need to be mindful that the raw engineering numbers never tell the whole story, and that as a result, that story can turn out to be very different depending on additional circumstances. Any minor new and seemingly unrelated invention, or even cultural change in how transport or commuting is viewed, can alter the future of any of these systems. Realistically, the basic notion of a lower pressure or vacuum transport system is not to save fuel at lower speeds, though that can be a powerful tool for mass cargo transport. It's more about permitting high-speed point-to-point transport between hubs and at speeds near or in excess of the sound barrier at normal pressure. This is the same reason planes fly so high, with less air drag. In a more distant, hyper-efficient society, it might be used for fuel-saving freight, and in a post-scarcity environment, it could manifest as underground vacuum tubes running right to an individual home. Indeed, pneumatic tubes, which use air pressure differences to push cargo in a pod, have been considered as an option to install in houses or individual apartments as a means of mail and package delivery, much as we often consider automated drones for that nowadays. A vacuum tube big enough for a passenger vehicle is obviously a big step up. Strictly speaking, a pressure vessel underground isn't using any more material than a driveway. It is more sophisticated to build and maintain, but we must not assume that to be a barrier forever. The lower floor of my house has radiant heat and carpet in my studio where I'm writing this, a bunch of little tubes carrying around hot water, which is pretty sophisticated compared to the dirt floor my not too distant ancestors had. And indeed, even carpet is pretty sophisticated stuff in the absence of modern machinery. In the context of large future societies where our numbers might have grown and real estate gotten to such a premium, we build mega skyscraper ecologies or artificial space habitats for more living space. The idea that those might have lots of local hubs or even individual connections to vacuum tunnels is not too hard to fathom. It may be costly to go underground to build transportation if the alternative is to stay on the surface, but if you're building the ecology from scratch, you're building it anyway. Same as your elevator shafts. Same goes for air. If your ecology is designed to be built anywhere on the planet from tropics to Arctic, it probably has air pumped in to maintain desired air pressure and composition, in which case it is quite easy to just not pump that into some tunnels. I should also note that one of the challenges I've heard about Hyperloops is that we can't build a tube that wide that has a different pressure. As mentioned, there are legit hurdles and objections to these sorts of systems, but this is not truly one of them. It is a serious engineering challenge to do it economically, and we won't dip into that today, as others have discussed it more, but I've seen a lot of folks on the internet imply it's physically impossible. It is not, and for some current examples, for higher pressure within than without, we of course routinely do that with pipelines, though routine does not mean easy. For the other way around, lower pressure inside than out, that's called a submarine, and they are a lot wider and deal with a much larger pressure differential than some transport tubes. And while saying we're going to run a tube at 1,000th of Earth normal pressure might sound impressive, remember that a tube with that inside and normal air outside requires no more strength than a tube sitting 10 meters underwater would, with normal air pressure inside and 2 atmospheres of pressure in the water outside. And we do have a lot of structures that exist in far deeper and higher pressure situations. Again, this does not mean there aren't engineering challenges involved in trying to build a 1,000-mile long tube under pressure that pods will be moving down at very high speed, all while that train gets rained on or hit with a wind gust or is undergoing constant temperature variation to expand or contract. That's why an actual vacuum train in space, or one buried underground where there's no weather or temperature changes, is much easier, especially if you have a cheaper way to dig tunnels than we currently do. But there's solutions for all those problems. It's just trying to find which one is best overall in cost, safety, and simplicity. As an example, there are concerns about individual segments expanding thermally and that being a hard problem to solve, and that likewise is a well understood problem in engineering that we can handle with expansion joints, and which requires tweaking to use in the actual vacuum of space, where heat comes and goes only by radiation rather than convection or conduction, except conduction along that tube, of course. I should also note that while folks tend to visualize these as some clear glass cylindrical tube running above ground, it could just as easily be a wide arched tunnel underground with several rail lines running down it, just like any other transport tunnel we build nowadays. I do not want to be too blasé about that. Things like airlocks are tricky and costly additions, and you also need to run pressurized vessels inside these evacuated tubes so people don't die on the trip. We also need to know what our ideal speed is before we decide the pressure inside the tube though, because while any drop in air pressure, or more accurately air density, is going to lower your air drag, the speed of sound drops a bit as pressure does too. That's for air though, and I should note that heliox, a mix of helium with some oxygen, is a popular suggestion for filling such tubes, and we should be mindful that helium is super abundant in the universe and our solar system. It just doesn't like to hang around Earth. Big tankers from Jupiter or Saturn might deliver it here or to various other human habitats for such uses in a future interplanetary economy. A helium-filled tube is obviously not a vacuum tube, and if you are wondering, the reason is that you can run a heliox tube at the same pressure as a normal air tube and have way less air drag. Helium is also chemically inert, so you don't have to worry about it corroding things or minimal leakage of it into your travel pods having any other effect on people beyond making their voice a bit higher. And your voice is higher in helium because the speed of sound is about 3 times higher in helium too, raising that sound barrier limitation. The frequency of your voice, or any wave, times the wavelength equals the speed of waves in that medium, and you can calculate any of those if you know the other two. It's a debatable point, but I lean toward near vacuum as better than filling things with other gases, and of course that's only when on a big planet with an atmosphere. On places like the Moon, which is airless, or Mars, with its very low air pressure, your vacuum tube is only a tube to keep dust from getting on your track and either messing up your low friction rail or damaging your maglev equipment, as is already vacuum or nearly so. On some planet with stronger gravity, you might have significant helium still in the atmosphere and then it's cheap to use too, so it just depends on the location. We assume this is fairly standard equipment for any orbital megastructures, especially big conglomerations of them that we often imagine for collections of O'Neill cylinders and their associated or ancillary facilities. This might be a simple tether you ran down, or it might be a tube. Even in vacuum, it can be good to have some protective layer between you and the void. You also need some mass to be pushing and pulling on, so even if you have super strong tensile materials that can handle a train's mass on a hair-thick tether, it makes things easier to go thicker or have a tube to shove on. Though the more contact points you have, the more friction, which is why a magnetic field is preferable for that. So there are valid options for space applications, but they're also good for getting into space. We touched on that application more in our episodes on mass drivers and interplanetary infrastructure. But the basic notion is that you can build a giant launch ramp into space using an evacuated tunnel that exits over the atmosphere, as we see with Startram's design. A lot of folks prefer the engineering of a platform that begins and ends above the atmosphere, that you can reach by tether or elevator, and that's the launch mechanism used in the Lofstrom loop, the tethered ring, and the orbital ring. This is also our default approach to them on places like Venus or Titan, with very thick and dense atmospheres where a tube might float on balloons. Needless to say, if I can launch something up into space without rocket fuel, that's a huge savings. Assuming I can put enough traffic through that to justify the construction and maintenance costs. You will never get things into space for the actual kinetic energy they need to orbit there, but you can get a lot closer with this method. As an example, a person with a suitcase whose combined mass is 100 kilograms needs about 3.2 billion joules of kinetic energy to orbit Earth, which sounds like a lot, but it's about the same energy as in a year worth of the typical human diet, or a couple tanks of gasoline, or half a barrel of crude oil. whereas those big modern rockets blow through 1 million pounds worth of fuel per launch to get a few folks into orbit and not much more cargo up there. A mass driver or vacuum train isn't going to let you get yourself into orbit for 1 barrel of oil, which is trading as I write this for $78 a barrel, but it's able to get you into orbit for that order of magnitude, so that flying to space costs in the same sort of fuel ranges as driving or flying across country. Which is why we contemplate these for ground transit, as it means getting from one side of a continent to another faster than the plane can get you there, and for less fuel than we get from ultra-efficient but slow freight trains, which themselves tend to do as good as 500 miles per ton of cargo per gallon of fuel, and are an order of magnitude more efficient than even modern cars. So our vacuum train aims to do even better than that for fuel efficiency, while outpacing a supersonic jet. This is the fundamental appeal to them, and why the idea tends to have a lot of momentum in spite of the engineering and right-of-way issues. And I would say the right-of-way issue is the bigger of those two problems currently. Now that gets us to the notion of a gravity train, and the simple conceptual notion is to cut a hole right through the center of the planet and evacuate it, so if you drop down it, you'd accelerate on the way to the core, and then decelerate as you rose up to the surface on the other side, all from gravity and needing no more fuel or energy than whatever was lost to friction. Ignoring the issues with driving a tunnel through the center of your planet, which we discussed more in our episode Accessing Earth's Core, Earth is actually one of the best places to make such a tunnel, as is the densest object we know of in the solar system, and density controls your acceleration in vertical tunnels. The time it takes to fall, assuming a sphere of uniform density, is a formula that dates all the way back to Sir Isaac Newton and his original work on gravity, physics, and calculus. Needless to say, worlds are rarely of uniform density, but it tends to give a decent approximation. And for the Earth, that trip is about 40 minutes each way, or about 80 minutes to fall through a tunnel to the other side of the planet, and then back to where you left, at a peak speed of 8 kilometers per second. Non-coincidentally, it's a travel time similar to one orbit around Earth at low altitude, and with near identical peak speed. You are essentially on a high eccentricity elliptical orbit, the one in which the mass pulling on you diminishes with radius, so don't try to plug that into Kepler's orbital equation. Alternatively, on the Moon, with a radius of 1.7 million meters, around a quarter of ours, and a surface gravity of 1.6 meters per second, that gives us a time of 3,250 seconds, or 54 minutes, and in our episode Moon, Megacity, we discuss this technology in more depth, pardon the pun, since it's easier to dig there. I think you wouldn't just drop though under gravity, but opt to accelerate and decelerate magnetically on the journey to boost the effect of gravity. You may also be using this as a launching device to space on smaller bodies. That said, while that can work on smaller bodies like asteroids or moons, we really mean these to run on tangents through the skin of a planet, not through magma in a molten core. You can build a lot of speed up by dropping a single kilometer in a vacuum tube to run along a low-friction track buried underground. In a vacuum, it would take you about 14 seconds to drop a kilometer, and you would have a speed of 140 meters per second, or 313 miles per hour at the bottom, which is quite respectable for traveling around the planet. We have dug tunnels and mines a lot lower than that too, and we may opt to make such tunnels deeper, allowing a longer fall and thus faster travel, but you have to fall 4 times further to get twice the speed, and 9 times further to get thrice the speed, so there's going to be a practical cutoff, and probably at less depth than we can actually go. We can also still accelerate in such a vacuum tunnel. We are not limited to gravitational freebies, they just make it cheaper. I think digging tunnels that deep is not going to be cheap itself, but it might circumvent a lot of right-of-way issues trying to build on or near the surface. It's not hard to imagine us having such tunnels all through various low-gravity bodies, where less effort is needed to hold the tunnel up or keep a vacuum on it. But as we discussed in Domes of Mars, super strong materials like diamond and graphene are just carbon, a very abundant substance, and indeed one more abundant in our atmosphere than we prefer. And we can make them in the lab and have discussed sequestering carbon by making such materials, so we could easily have costs on mass manufacturing them drop the way they did on steel or aluminum in the past, and then your equation for a lot of building projects shifts hugely. As such, on Earth, it's a bit harder to say if such tubes would ever be practical enough that we dig them everywhere. Realistically, I think if we're making underground vacuum tunnels on Earth, our focus would be on putting them wherever the engineering worked best, which would vary on location. Much like highways and railroads, we can bend around as needed but try to keep it straight. That's a lot more important for high-speed vehicles too, as your safe turning radius rises sharply with velocity. I think you would want to dig well under whatever the common building depths were, which might mean hubs in cities dip down quite a bit, while we might even run them just under the soil in some places or even overground. I don't think we care as much about the free energy to speed up, because on a normal track there will still be some friction, and on something like a maglev train over superconducting magnets you can still do regenerative braking to pull some of that energy back. So the gravity train only works in a vacuum train context, otherwise you are still dumping in tons of energy to maintain speed, but that same setup makes the gravity aspect rather secondary, at least on Earth and for transport of people and parcels, because the lack of friction and the need to constantly apply energy to maintain speed just so overwhelms the free speed up from falling down. Still, I could see mass freight being done this way and by deeper tunnels, and ones that made use of thermocouples and the large temperature increase at greater depths to provide your power for maintaining that tunnel. We could also imagine it for very high acceleration rates to launch objects, where even a minimal curvature such as a planetary surface represents too sharp a turning radius. You might run a tunnel underground in a near straight line from LA to an opening in the Atlantic Ocean that rises above the atmosphere, where after 10,000 kilometers and a 10g acceleration rate, you are hitting space at 44 kilometers per second after just over 7 minutes. Very much a nice and usable interplanetary speed, and we have lots of cargo that could handle a 100g acceleration and come out of that tunnel into space at 140 kilometers per second. While raw materials like metal ores might easily handle 1000 Gs and emerge at 440 km per second. That is sufficient for interstellar travel, albeit the really slow kind we only contemplate for shipping of raw metals or other substances that time doesn't take much of a toll on. So as we can see, these are handy everywhere, and whether or not you build them just depends on how cheap and sturdy you can make your infrastructure. It's a no-brainer on megastructures simply because those only exist if the answer to the cheap and sturdy question is yes, very, as stringing some tunnel on the outside of your massive county-sized pressurized can sitting in the vacuum of space is about as big a feat as running an electrical wire through your home, compared to building and decorating it, and it lets you cut down on roads inside your habitat. This means most folks living in a cylinder habitat probably have basement access to various trains, though you might still run tethers up the central axis too. And while we say trains, you don't need to be that much more sophisticated to go for individual pods, or even something a person in a spacesuit could travel along. These are going to have a maximum speed though, and I think we can say well short of relativistic. Any accident inside one, on the outside of a rotating habitat, is blowing most of that force out and away from the station. But not all of it, and some 10-ton cargo pod moving at 1% of light speed, even if only 10% of its energy is going into the walls, is still hitting like a megaton nuke, which your hull might be designed to handle without catastrophic rupture with damaged or hijacked spacecraft in mind, but probably is on the high end of what you'd even consider for any transport tube. I'm guessing by at least an order of magnitude, and moving at 1,000th of light speed instead is very sufficient for travel around even enormous megastructures like Banks orbitals on Niven Ringward or even a Topopolis. And a cool thing about them, as we discussed in interplanetary infrastructure, is that you might build your rail lines between planets themselves, which requires some additional engineering tricks, but is doable under known science. See that episode for details. So I don't know when vacuum or low-pressure tunnels are going to emerge on Earth, probably before we build many off Earth, but I'm confident the future of transportation will see lots of vacuum trains speeding along and carrying us around and off our pale blue dot into the galaxy beyond. Today we were talking about how vacuum trains might be vital for moving around big megastructures like ring worlds, and one megastructure that would really need vacuum trains is a Topopolis, a rotating habitat that's essentially a very long O'Neill cylinder, many miles wide but potentially thousands or even millions of miles long. But you might also travel inside one more conventionally, and the Topopolis seems like it would inevitably have one long river running down its whole length, like a giant 4-tower river valley civilization of incomprehensible length. In this month's Nebula exclusive, Topopolis, the Eternal River, we explore these megastructures and what they're like inside. Join us in a journey down a river so long it traces out 1,000 worlds as we explore a megastructure buildable with known science and materials, but of unbelievable proportions. And again, that's out now exclusively on Nebula, our streaming service, where you can also see every regular episode of SFIA a few days early and ad-free, as well as our other bonus content, including extended editions of mini-episodes and more Nebula exclusives, like last month's look at giant space monsters, December's episode The Fermi Paradox Hermit Shoplifter Hypothesis, ultra-relativistic spaceships, dark stars at the beginning of time, life as an asteroid miner, nomadic miners on the moon, space freighters, retrocausality, OR and free will, colonizing binary stars, and more. Nebula has tons of great content from an ever-growing community of creators. Using my link and discount, it's available now for just over $2.50 a month, less than the price of the drink or snack you might have been enjoying during the episode. When you sign up at my link, go.nebula.tv/IsaacArthur and use my code IsaacArthur, you not only get access to all the great stuff Nebula offers, like Topopolis, the Eternal River, you'll also be directly supporting this show. Again, to see SFIA early, ad-free, and with all the exclusive bonus content, go to go.nebula.tv/IsaacArthur. Next week we'll be finishing the month of February on the 29th with a journey to a colony Ark ship that is itself journeying to new worlds, and yet in which entire cultures might exist for generations on board one, and we'll ask what life on an Ark ship is like. That will take us into March, where we'll begin by heading to the beginning of time for a look at primordial planets. Then we'll continue our discussion of terraforming from earlier this week when we looked at terraforming our own moon by asking if and when terraforming in general is ethical and what sorts of challenges future civilizations will face on deciding whether or not a planet should be terraformed and to what degree. Then we'll travel toward Mars to look not at the red planet but instead at its two tiny moons, Phobos and Deimos, and ask why and how we could settle them. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you'd like to donate or help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, along with hours of bonus content like Topopolis, the Eternal River, at go.nebula.tv/IsaacArthur. As always, thanks for watching and have a great week.